When engineers discuss PFAS and micropollutants, the conversation often begins with a number, a laboratory result, a detection statement, or a comparison against a specified analytical list. But before that number is interpreted, one question must come first. What exactly was measured? The United States Environmental Protection Agency identifies methods 533 and 537.1 as methods that help laboratories measure 29 PFAS compounds in drinking water. That is important analytical capability, but it is not the same as measuring every member of the PFAS chemical family. A targeted method answers a targeted question. It does not automatically answer a broader question about all PFAS or all micropollutants. For a technical audience, this distinction is not a footnote. It is the starting point for defensible monitoring. A result may be precise within the scope of the method, while remaining incomplete with respect to the larger universe of compounds. Therefore, the phrase "not detected" must be handled carefully. Within the method and its quality controls, it means the analyte was not detected at the relevant reporting capability. It should not be casually translated into zero, nor should it be presented as proof that the broader chemical family is absent. This episode follows that principle from the laboratory to the treatment process. We will look at monitoring, sampling quality, activated carbon, ion exchange, and high-pressure membranes. We will also follow the contaminant mass after it leaves the water phase, because a treatment system can transfer a contaminant into another stream without destroying it. PFAS should be treated analytically as a family of compounds, rather than as a single universal indicator. The practical consequence is that monitoring design begins with scope. Which compounds are included? Which method is being used? What quality controls support the result? And what question is the result intended to answer? The research basis for this episode does not support presenting one measurement as a complete description of all PFAS. It supports a more disciplined interpretation. Targeted analysis can establish information about the compounds included in the method, while leaving open the question of compounds outside that target list. This is why a professional report should state the analytical scope, rather than rely on a broad phrase such as PFAS-free. The same logic applies to the phrase micropollutants. It is a useful category for substances present at low concentrations, but it does not remove the need to define the analyte, the method, and the matrix. A low concentration does not make a measurement interpretation free. The water matrix, the sampling process, and the laboratory quality system still matter. For engineering communication, the most reliable language is explicit language. Say what was measured, by which recognized method, under which quality controls, and what remains outside the evidence. This approach is not unnecessarily cautious. It is how a technical team prevents a narrow result from being expanded into a claim it cannot support. The treatment decision must follow the same discipline. A removal technology is not selected because it is associated with PFAS in general. It is evaluated against the compounds of concern, the properties of the water, the operating context, and the residual stream that the process will create. EPA identifies granular activated carbon, ion exchange, and high-pressure membranes as treatment technologies studied for PFAS removal. Their performance can differ with the compound, water characteristics, and operating conditions. A sophisticated treatment discussion is only as credible as the sampling and measurement process behind it. The research basis emphasizes the need to prevent background contamination and to apply quality control during sampling. For PFAS work, that means the sampling plan must be understood as part of the analytical system, not as a separate administrative step. The purpose of contamination control is straightforward: prevent materials, handling practices, or the sampling environment from introducing PFAS into a sample or otherwise compromising its interpretation. The exact controls belong in an approved laboratory and project quality system. This episode does not provide facility-specific procedures. The principle, however, is universal. If background contamination is not controlled, the resulting data may be difficult to distinguish from the condition being investigated. Quality control also protects against overconfidence in a single result. A professional monitoring program considers the relationship between sampling, laboratory analysis, method scope, and data review. It asks whether the result is consistent with the intended method, and whether the evidence is sufficient for the decision under consideration. It does not turn a laboratory value into a universal statement without checking the boundaries of the measurement. For engineers and technicians, the key message is that monitoring is not merely a data collection activity. It is a chain of evidence. Break the chain at sampling, quality control, analytical scope, or interpretation,
and the apparent precision of the final number can be misleading.
High-pressure membranes, including reverse osmosis and nanofiltration in the research framing, use pressure-driven separation to divide the feed into streams. From a water quality perspective, the attraction is clear. A treated stream can be separated from a stream in which constituents are concentrated. From a systems perspective, that second stream is central, not incidental. The presence of a concentrate changes the engineering question. The process may reduce the PFAS concentration in one water stream while increasing the concentration in another. That can be an effective separation step, but it is not the same as destruction. The concentrate, therefore, requires its own evaluation, management pathway, and appropriate professional oversight. Membrane performance also depends on the water and the operating context. Treatment performance varies with the PFAS type, water characteristics, and operating conditions. Consequently, a membrane result from one test cannot be presented as a universal guarantee for another matrix. The relevant evidence must represent the conditions being considered, including the characteristics that may influence separation and fouling or other process behavior. A technically honest visual should show both sides of the membrane, the treated stream and the concentrate. It should not imply that the contaminant disappears at the membrane surface. The most important graphic is a mass balance: what enters, what leaves in the treated water, and what remains in the concentrate or other residuals. This is also where treatment selection becomes a life cycle question. The choice is not merely about a unit process. It includes monitoring, residual handling, verification, and the consequences of changing feed water conditions. The exact design and operating decisions belong to qualified teams working within site-specific requirements. This episode remains at the level of principles. This is the central lesson of PFAS treatment. Removal from water is not the same as disappearance of mass. Technologies applied in the field for liquids often depend on capture or separation and do not necessarily destroy PFAS. For granular activated carbon and ion exchange, the mass can be associated with spent treatment media. For high-pressure membranes, it can be concentrated in a separate liquid stream. These are not identical residuals, but they share a systems implication. The treatment train must account for what happens after the water phase concentration changes. A narrow performance claim may say that a treatment process reduces PFAS in the treated water. A complete engineering discussion asks where the PFAS goes, how that residual is characterized, and which management pathway is appropriate under the applicable requirements. The research does not provide a universal disposal solution, and this episode does not invent one. This mass balance perspective also prevents a common communication error. A chart that shows only influent and effluent can create the impression of destruction, even when the process is primarily a transfer. The visual language must therefore distinguish among capture, separation, concentration, and destruction. These terms are not interchangeable. Technology selection becomes credible when it is tested against the water that the technology will actually encounter. The research calls for testing site water and considering its changes over time, including seasonal variation and organic matter. This is a practical reminder that a treatment result is inseparable from its metrics and its conditions. Seasonal change matters because the water presented to the process may not be constant. Organic matter and other characteristics can influence how a treatment medium or membrane behaves. The exact effect must be established through appropriate site-specific evaluation, rather than assumed from a generic product description or a result generated under different conditions. Technology maturity provides useful vocabulary. Technologies can be field-applied, limited in application, or emerging. That vocabulary helps technical teams separate evidence categories. A field-applied technology may still require site evaluation. A limited application technology may have relevant evidence, but a narrower track record. An emerging technology may be technically promising while requiring further assessment of readiness, performance, and residuals. A professional video should resist the temptation to fill the screen with a universal percentage. The more responsible message is that performance is conditional, measurable, and bounded. The treatment technologies discussed in the research are best understood first by their basic function. Granular activated carbon and ion exchange are media-based approaches. High-pressure membranes are separation approaches. These descriptions explain the treatment pathway, but they do not guarantee a universal performance level. The Environmental Protection Agency identifies activated carbon, ion exchange, and high-pressure membranes as technologies studied for PFAS removal. The expected performance differs with the type of PFAS, the characteristics of the water, and the conditions under which the process operates. This is why a technology comparison should not be reduced to a ranking that ignores site conditions. A useful engineering frame is the breakthrough curve. For a media process, the treatment effect is not a permanent label attached to the vessel. It changes as the medium interacts with the water and approaches its capacity under the relevant conditions. The curve is therefore a way to think about changing performance over time, not a promise of a fixed removal percentage. The same caution applies to membranes. A membrane can separate components between a treated stream and a concentrated stream, but the contaminant has not necessarily been destroyed. The treated water and the concentrate must be considered together in the mass balance. There is also a difference between a technology being discussed, tested, or demonstrated, and being broadly mature for a particular field application. Technologies may be applied in the field, have limited application, or remain emerging. Each technology must be evaluated under site conditions. The professional question is therefore not simply which process removes PFAS. It is which process, under which water conditions, for which compounds, with which residuals, and at what level of demonstrated maturity. Granular activated carbon, or GAC, and ion exchange, or IX, illustrate why the word removal must be paired with a mass management discussion. Both approaches are associated with capturing or retaining contaminants in a treatment medium. That can reduce the concentration in the treated water, but it also means the medium becomes part of the PFAS management problem. The relevant performance question is not only the initial treatment effect. It includes how the medium behaves with the actual water, how competing constituents influence the process, how performance changes over time, and what happens when the medium is spent. Water characteristics and operating conditions affect performance. For a professional audience, the breakthrough curve is a better mental model than a single headline removal number. At the beginning of a treatment line, the relationship between the medium and the influent may produce one level of performance. As the medium is used, that relationship changes. The point at which the treated water concentration begins to increase is not an abstract chart event. It represents the need to understand capacity, monitoring, and residual management within the approved design and operating framework. Ion exchange follows a different interaction principle from activated carbon, but the same engineering discipline applies. It must be assessed against the compounds, the water matrix, and the intended application. A result obtained in one water should not be transferred automatically to another water without testing and technical justification. Most importantly, neither a spent carbon bed nor a spent ion exchange medium should be treated as proof that PFAS has vanished. Field-applied liquid treatment technologies often rely on capture or separation and do not necessarily destroy PFAS. Therefore, the water phase result is only one part of the treatment story.
The evidence supports a disciplined conclusion, rather than a universal answer. First, measurement must be interpreted within the scope of the method. Recognized laboratory methods can support measurement of specific target compounds, but they do not necessarily represent an entire chemical family. Second, treatment performance is conditional. Activated carbon, ion exchange, and high-pressure membranes are studied treatment pathways, and their behavior varies with compound type, water characteristics, and operating conditions. The correct comparison is therefore not a slogan about the best technology. It is a site-specific evaluation of treatment objectives, evidence, residuals, and maturity. Third, capture and separation must not be confused with destruction. A lower concentration in treated water can coexist with PFAS in spent media or concentrate. The treatment train is a system, and the mass balance continues beyond the outlet of the primary unit. Fourth, sampling quality is part of engineering quality. Background contamination,
Quality control, method scope, and data interpretation determine whether the evidence is strong enough for the question being asked. The result should be communicated with its boundaries, not detached from them. For engineers and technicians, this is not a call for inaction. It is a call for precision. Define the analytes, protect the sample, test the actual water, consider seasonal change and organic matter, track residuals, distinguish field application from emerging development, and never let a visually impressive removal claim outrun the evidence behind it. PFAS and micropollutants demand this level of care because the hardest part is not naming a technology. The hardest part is connecting measurement, treatment, mass balance, maturity, and uncertainty into one defensible technical story. That is the standard this episode recommends.